What if we could stop treating diseases and start programming our own bodies to fight them? It sounds a little like science fiction, right? But we are right on the cusp of a new era where biology isn't just something we observe, it's something we can engineer. And this is all happening because of a few key technologies coming together in a really powerful way. So let's just start with that big idea. What if programming biology was as precise as programming a computer? Well, that question is no longer just a hypothetical. It's becoming our reality. And today we're going to break down exactly how. Okay, so our story really begins with an incredible AI called AlphaFold. You can think of it as a kind of digital microscope, one that lets us see the actual machinery of life. And believe me, it is the key that unlocks everything else we're going to talk about. And this whole revolution is happening at a truly astonishing speed. I mean, just look at this timeline. In 2018, we got AlphaFold 1. Then, just 2 years later, boom, AlphaFold 2 was a revolutionary leap. And now, in 2024, another massive shift with AlphaFold 3. We're not talking about small, incremental steps here. These are massive, exponential jumps forward. So what can this new AlphaFold 3 actually do? Well, this quote just nails it. It's a digital microscope that lets scientists see the molecular handshake, the exact way that proteins and DNA and even drugs all interact with each other, right down to the atom. Honestly, this is like the biological version of seeing the universe for the first time through the James Webb Telescope. It's a whole new view. Now, what's really cool is how it works. See, AlphaFold 2 was what we call a discriminative AI. Think of it like a detective who's really, really good at picking the right suspect out of a lineup. It shows the most likely protein shape from a bunch of possibilities. But AlphaFold 3, it's generative. It's more like an artist starting with a blank canvas. It just begins with this random cloud of atoms and then sculpts it into the most chemically perfect 3D structure. And that is why it's not just limited to proteins, it can model pretty much any molecule you throw at it. So what's the real-world impact of all this? How about a 50% jump in accuracy when predicting how a new drug will interact with a protein in your body? That isn't just a little better. It's a massive leap that could completely change how quickly we discover new medicines. And just to give you a quick peek under the hood of its predecessor, AlphaFold 2, it was an engineering marvel. It had these different modules working together, one processing data and the other building the 3D model. We won't get lost in the weeds here, but the main takeaway is that AlphaFold 3's new generative approach has evolved way beyond this, making it an even more flexible and powerful tool. All right, so we've got this incredible new way of seeing biology. So what do we do with it? Well, let's take a look at one of the biggest challenges in all of medicine, cancer. Because it turns out, when you can see a problem this clearly, you can start to engineer a solution that's just as precise. And the key to this whole new strategy is something called a neoepitope. The best way to think of it is like a tiny, unique, wanted poster that only shows up on cancer cells. It's a little flag that pops up because of the tumor's genetic mutations. So if you can train the immune system to recognize that specific flag, it can hunt down and destroy cancer cells while leaving all your healthy cells completely alone. And this is not just a theory, folks. This slide shows a real-world clinical trial for a very aggressive type of brain cancer. They're basically using a three-pronged attack. First, there's a vaccine that teaches the immune system's T cells what that wanted poster looks like. Second, a drug to make sure those T cells don't get worn out during the fight. And third, a cream to kind of rally the troops and boost the immune response right at the injection site. It's this incredible personalized assault on the cancer. And the early results? They are seriously promising. The vaccines are safe, they're triggering the exact immune response they're supposed to, and this is huge. Those immune cells are actually getting past the blood-brain barrier to the tumors. We're even seeing some patients with no tumor growth for more than 2 years. It's a really powerful example of how understanding biology at a digital level can lead to major real-world breakthroughs. But here's the thing, this new era of personalized medicine creates a brand new challenge. Every single one of these custom treatments relies on a mountain of unique, incredibly sensitive patient data. So to make this all work at scale, we don't just need a medical revolution, we also need a data revolution. And the scale of this data problem is, well, it's kind of staggering. An estimated 80% of all healthcare data is just sitting there, unstructured and locked away in separate siloed systems. It's basically unusable. We're talking about a treasure trove of information that could help cure diseases, but we can't get to it. And this is where a technology you might not expect to hear about comes into play, blockchain. So why on earth blockchain? Well, this chart shows the main reasons it's being adopted in healthcare. The biggest driver right now is actually securing the drug supply chain, making sure medicines are authentic. But right on its heels are two other massive issues: cutting down on huge administrative costs and, critically, finally getting all these different electronic health record systems to actually talk to each other. Now, getting this tech into hospitals isn't a one-size-fits-all kind of deal. As this slide shows, there are a few different paths. You've got your big institutions that just go all in, then you have some who have the right tech but face a lot of internal pushback. For smaller clinics, there are cloud-based solutions that are easier to adopt. And sometimes, everyone gets pushed into the future by new regulations like GDPR. Okay, so we have this incredibly powerful AI, and we have this super secure decentralized data network. The real magic happens when you put them together. You see, AI needs huge amounts of data to learn, but that data is often super sensitive. Blockchain is great at security, but it needs a killer app to be truly useful. They basically solve each other's biggest problems.
And that brings us to the absolute critical question. How in the world do you train a powerful AI on all this sensitive patient data from different hospitals all over the world without ever violating anyone's privacy?
The answer is this really brilliant idea called federated learning. The best analogy is a traveling teacher. So instead of all the students, the data, having to travel to one central school, the teacher, the AI model, travels to each student's home. The AI trains locally at each hospital on their data, and then only the lessons it learned, totally anonymous insights, get shared and combined. The raw patient data never ever leaves the hospital. And that is where blockchain becomes the missing piece of the puzzle. It provides the secure, verifiable, and tamper-proof record that makes this whole federated learning system trustworthy when you scale it up. It's the trust layer for the entire operation. So, when you put it all together, this powerful AI, this secure data infrastructure, where does it all lead? We're not just talking about slightly better treatments anymore. We're witnessing a fundamental shift in what medicine even is.
This quote really says it all, doesn't it? Biology is transforming from an observational science, where we basically just described what we saw, into a predictable, programmable engineering discipline. That right there is the core idea of the programmable body. And it doesn't stop there. The next goals on the horizon are, frankly, mind-blowing. Imagine creating a perfect digital simulation of a human cell, a virtual twin we could use to test new drugs with near-perfect accuracy, or building self-driving labs, where robots run experiments 24/7, accelerating discovery at a pace we can't even comprehend. As this diagram shows, what started with one thing, predicting protein structures, is now exploding out into every corner of biology and medicine. We're not just watching biology anymore, we are actively designing it. We're creating new drugs, engineering new proteins, and building personalized vaccines. This technology is becoming the engine for a whole new era of discovery. And so that leaves us with one last really big question to chew on. With these self-driving labs coming, what happens when the entire scientific method, from forming a hypothesis to running the experiment to drawing a conclusion, can just run on its own in a continuous automated loop? What will we discover when the speed of science is no longer limited by us, but only by the speed of a computer?